till the previous lecture we were discussing the relationship of inversion charge and surface potential. Now we will discuss the relationships of current and surface potential and drain and gate voltages. So, now we will use all the previous work that we did to understand the relationship of terminal voltages and currents in different regions of operation, moderate inversion, strong inversion, etc. So, first we will derive a very drain current expression from a very fundamental treatment and which is valid for different regions of operation, and then we will use the idea of forward and reverse currents and their superposition to obtain drain current in different modes of operation, and then we will use our ideas of linearization based on the charge linearization that we have discussed till now. So, when we discuss currents, fundamentally currents are because of drift or diffusion. So, if we discuss drift current, then it is the current density Jn. We are discussing electron current density. So, this is a p type substrate that we are discussing, which since we are discussing n channel MOSFET. So, Np drift velocity into charge. So, this is what would be the drift current. What about diffusion current? Kt by q mu n, this is the diffusion constant. So, in the x direction, if the electron density increases, then there is a current in the x direction, conventional current in the x direction. So, this would come this way. So, now we want current and not current density. So, when we look at a MOSFET from the top, then it is the we would integrate the value of electron density from say 0 to y, 0 to z. So, this if z is the depletion width, this we would call Qi, is not inversion charge density per unit area looking from the top. So, then how does this convert into current, or we would like to call it ID, is not it, because it is a drain current. How would we like to relate it to current? Inversion charge into what is drift velocity? Electric field, x direction is from source to drain, it is the positive x direction. So, this is the electric field minus d chi s by dx into mobility to q. So, this is the current because of drift, and current because of diffusion again diffusion constant, inversion charge, how it varies with x direction. Since the inversion charge is negative, therefore, since the inversion charge is negative, an increase in inversion charge would give rise to a positive conventional current. Since charge is included in Qi, we do not need Q here, and the device would have a width W, then we multiply with this with the width W and also this with the width W. Since this is a positive charge, the minus Np into Q when integrated, and the charge is Q is negative, and therefore, a positive sign would come here. So, if we combine both of them, the drift and diffusion components, then the current ID would be, take out mu n W d chi s by dx plus ut, kt by q is ut, dqi by dx. Now, let us see what is the value of Qi, inversion charge. Now, we are taking charge sheet approximation. Qi is a sheet charge. So, since it is a sheet charge, it is dependent only on the surface potential. Its value is dependent only on the surface potential, and we would say that Qi is proportional to exponential surface potential minus phi f minus V. You can justify this by looking at the band diagram. So, if we draw the band diagram for this metal oxide silicon, near the source the bands would, suppose the bands are this near the source, with this being the Fermi level, okay, and near the drain the bands would bend more because drain to source voltage, suppose it is positive, and where would the quasi-Fermi level be? So, for the electron quasi-Fermi level, the electron quasi-Fermi level would move down by a value V or Vd, where this is QVd, okay. Source voltage is 0, Vd is non-zero and positive, okay. So, in such a case you would have the, so this would be, this blue one is Fp whole quasi-Fermi level and the other one is Fn, the electron quasi-Fermi level. So, you can justify this from here. So, the band bending is chi s, the overall band bending is chi s near the drain, suppose here. So, this is chi s, and from that you remove phi f because that gives rise to Ni. So, I mean Ni e to the power phi f by ut is Np. So, here in the background you have Np is equal to Ni e to the power minus phi f by ut. So, based on that you get this, and this V is because Fp minus Fn quasi-Fermi level of electron and hole, they are different by QV. Based on these two you get this expression, which we had discussed in the earlier lectures. So, now let us try to figure out what is this drain current. So, if we take this into account, this relationship into account, then dqi by dx would be qi into d chi s by dx minus dv by dx. So, what is this V? V is local channel potential because of drain voltage, which has developed because of drain voltage. What is chi s? It is the total surface potential. Okay. So, how are these two different? So, at the source edge the surface potential is chi s. Suppose as you move towards the drain, the surface potential increases. So, at the drain edge the surface potential would be chi s s plus V d. So, it is the local channel potential which has increased. Okay. So, here we are discussing, this is surface potential and this is local channel potential. So, that is how these two are different. So, what is the value of ID? If we substitute this into this, what is the value of ID that you will get? Mu n W Qi dV by dx, a minus sign would appear because Qi is negative and ID is positive. So, a minus sign also appears. Now, let us try to figure. So, now this is a relationship of drain current ID with local channel potential. Now, the question arises, how do we get a drain current value which is dependent on terminal voltages for different regions of operation? We know that the current would be constant from 0, that is source, to L, which is drain, source edge to drain edge in steady state. So, if we integrate this from 0 to L and integrate this, assuming that the width and mobility are constant throughout. Now, this is a long channel device treatment that we are doing. So, therefore, you can safely assume the mobility, width, that all these things to be constant. So, what are the limits? Now, at the source you have source voltage Vs, at drain you have drain voltage Vd. So, you get a popular expression, ID is mu n W by L Cox integral 0 Vs to Vd Qi by Cox dV. So, Vs usually we assume it to be 0. So, that is how we have been doing till now, but to generalize let us take it to be some source voltage Vs. So, we can write this as mu n Cox W by L Vs to Vd Qi by Cox dV. This is called beta. This beta is called transfer parameter of MOSFET. Now, what we observe is we have taken a very fundamental approach. It is just the drift current and diffusion current that we have added up. So, now this is therefore valid in all regions of operation, that is subthreshold, that is weak inversion, moderate inversion and strong inversion. So, it is also valid in linear regime, saturation regime, etc. Now, let us make a few more observations. This now it would seem that the integral, this integral, now the limits are Vs and Vd. So, it would not depend on the shape of the variation of Qi with V. It would rather depend on the value of the integral at Vd and the value of integral at Vs. So, it is just depending on the boundaries of the region. If we identify this as the region, then it is just depending on the boundaries of the region. Now, we can identify from our previous lecture that what is this slope? It is minus n, because we had seen in the previous lecture that if we have V versus for a given gate voltage, V versus Vg or Vtb, this is the slope, n, this is Qi by Cox, minus Qi by Cox. So, from that we can easily identify this to be minus n. Now, the shape, so this is dependent not on the shape of this, how Qi varies with Cox, but it is dependent on Vs and Vd. So, what do we mean by this? So, this is as if you have superposition of two values, the value of integral at this point minus the value of integral at this point. So, what is the integral? Integral is Qi dV. So, the value of the integral here minus the value of integral here, as if there is a current flowing into this region and also a current flowing into this from Vd in an opposite direction. So, it is as if you are having superposition of two currents. So, this we will discuss further. So, you could have written the same integral Id as integral Vs to 0, Vs to infinity. What would happen at infinity? So, what would happen if the local channel potential V is infinity, has a value infinity? Inversion charge would tend to 0. This is an imaginary situation, but if the local channel potential keeps on becoming larger and larger, it means it has become larger than chi p, pinch off potential. You can assume this, so then inversion charge would tend to 0. So, we can now write our expression as Vs to infinity Qi by Cox minus Qi by Cox dV minus Vd to infinity minus Qi by Cox dV. So, what we have done is using since the value of the current is dependent only on the value of the integral at the boundaries and not on the intermediate values of Qi or intermediate values of the integral also, integral of Qi. So, we know that the value of Qi is 0 at for the local channel potential tending to infinity, and therefore, the integral value of the integral of Qi dV would also tend to 0 at when the local channel potential V tends to 0, but tends to infinity, I am sorry. So, using these two facts, we now break this integral into two parts this way, and we know that at infinity the integral evaluates to 0. So, we use that fact. So, conceptually it is as if there is a current flowing in the forward direction, source to drain, and in the reverse direction, drain to source. So, therefore, we call this forward current minus reverse current. This corresponds to the integral from source to infinity, and this corresponds to the integral from infinity to drain. Okay. So, we use this in further deriving the current expression. Before that, let us look at the different regions of operation of the device. Now, this is the discussion that we are having is valid for weak inversion, moderate inversion and strong. So, when we say forward saturation, as discussed here, the forward current is larger than reverse current. So, these three are like forward current is larger than reverse current. So, here when we say forward saturation, then the drain voltage, local channel potential at the drain edge is larger than chi p, pinch off potential. Okay. Suppose the device is operating in strong inversion, then we would say that in forward saturation, the drain voltage is larger than pinch off potential, and in triode region or linear region, the drain voltage is smaller than pinch off potential. Okay. And suppose you are operating in moderate inversion, so in forward saturation, the drain voltage would be larger than or equal to the pinch off potential chi p. So, in moderate inversion, the local channel potential is of the order of V p. It is close to V p, and therefore, you cannot neglect any of the terms to q I natural logarithm of q I. You cannot neglect both of them, both are significant, comparable. Now, in forward saturation, you would say that the drain voltage V d is close to chi p, pinch off potential, and in the triode, if we want to call it triode or linear regime, though it is strictly not. So, here triode like, so it is a forward saturation like and a triode like. So, there you would find that the drain voltage is again close to V p, pinch off potential. What is this reverse saturation? Here you are having just the, you flip the drain and source and you have similar relationships again. And what is this weak inversion? So, in weak inversion you would have the surface potential to be smaller than or maybe much smaller than V p, local channel potential for pinch off or the edge of strong inversion and weak inversion. Okay. Now, let us derive the an expression for current, which relates the local channel potential and the current in all the regions of operation. So, let us first define term called I specific, I spec, and that is mu n W by L U T Q specific, where Q spec we had defined earlier. So, what is this? Mu n W by L U T square N C of. Now, let us rewrite the expression for forward current or reverse current, both look similar. So, this is V s to infinity beta minus q I by C of d V. Now, you can rewrite this as beta V s to infinity minus q I plus q I by minus 2 n C ox u t, which is q specific into, so you multiply a u t here, you multiply 2 n u t. So, that brings you to the forward current being beta 2 n u t square integral V s, normalized V s now to infinity, normalized inversion charge q I integrated over normalized local channel potential V, where V is V by u t as we had defined earlier. So, what is this? I specific, I spec, normalized V s to infinity, normalized inversion charge integrated over normalized local channel potential. Now, let us look at this dV, because it is very hard for us to talk in terms of local channel potential. So, let us look at how we can better understand this dV. So, we already know that 2 Qi plus natural logarithm of Qi is Vp minus V. This we had derived earlier in our previous discussion, and this is valid across all regions of operation, weak inversion, moderate inversion and strong inversion. So, if we take an derivative on both the sides, now Vp for a given gate voltage Vp is a constant, pinch off local channel potential, pinch off potential, that is a constant for a given gate voltage. So, you get du Qi by dV into 2 plus 1 by Qi. So, we replace this with I specific integral. Now, Qi is this, and here you have, instead of dV you have 2 Qi plus 1 dQi. And where does it integrate from? Qi of source to at infinity, at the local channel potential being infinity, what is the value of Qi? 0. So, now if we define that have a normalized current If by I specific is the normalized current If, if we define it this way, then this becomes If normalized is equal to integral 0 to infinity, 0 to Qi at source to Qi plus 1 dQi. So, what is this? This is 2 Qi square by 2 plus Qi at source. You could also rewrite this Qi in terms of If. So, you could say that Qi at source is minus 1 plus square root of 1 plus 4 If, sorry, this is normalized If by 2. So, we can rewrite the expression that we already know, Vp minus V is equal to 2 Qi plus natural logarithm of Qi. Now, this is valid in all regions of operation. So, we can rewrite this expression. So, it is Vp minus Vs, source, the local channel potential at source. Now, what is this equal to? 2 times square root of 1 plus 4 If minus 1 plus natural logarithm of square root of 1 plus 4 If minus 1 minus natural logarithm of 2. So, the expression turns out to be Vp minus Vs is equal to square root of 1 plus 4 If plus natural logarithm of square root of 1 plus 4 If minus 1 minus 1 plus natural logarithm of 2. Now, what is this? Let us see. You could have also generalized this by saying that this is source local channel potential or drain's local channel potential, and if it is drain local channel potential, then this is replaced by the reverse current, isn't? So, now let us try to understand what is happening here. Suppose the device is operating in strong inversion regime. Value of If would be quite large, strong inversion linear regime. Value of If would be quite large, and since the value of If is quite large, this would dominate and this term can be neglected. So, it is this which dominates them. But on the other hand, if the device is operating in, suppose, saturation regime, for If this would dominate and this would be negligible. For IR, your drain voltage is larger than Vp in saturation regime, and therefore, for IR this may become quite small because the drain voltage is larger than Vp, and then this would dominate. Okay. So, and it would be very small compared to If. So, it is If which you will consider. In moderate inversion, both the terms would dominate, would be important. In weak inversion, this would be very small and this term would dominate. So, we will use these in the next lecture to derive current values depending on the terminal voltages for weak inversion and strong inversion regimes. So, in this lecture, we discussed a very fundamental approach to obtaining current with respect to local channel potential, which is valid in all the regimes of operation of the device, of a long channel device, and we also used our earlier discussion on charge potential linearization to obtain an expression of drain current with respect to the pinch off potential and local channel potential, which is valid in again in all the regions of operation of the MOSFET. In the coming lecture, we will discuss how to use our today's work in obtaining expressions for drain current in weak inversion and in strong inversion regimes with respect the drain current with respect to terminal voltages. Thank you.